So I entitled my talk, System Safety and Policy Implications of Autonomy. And as Claire said, I'm an aviation guy, even though I used to work at JPL in the Advanced Devices Group. But anyway, it's going to be mostly an aviation perspective on this. So with that, I try to keep things simple, especially since went to industry for a while. And so I'm going to focus on three questions, which is, what is autonomy? And in that, of course, is our definition, or is the sort of common definition of autonomy a complete definition? Second question, what policy issues must be addressed to enable autonomy? And the last question, what framework should we be using to explore system safety within the context of autonomy? So I'll start with the first and start by saying it's always good to have a reference frame. So I'm going to give a little brief history of automation as a stepping stone to the definition of autonomy in aviation. And the one thing that you quickly realize when you start thinking about how long ago were we actually allowing machines to operate airplanes? And you realize that it was quickly, very soon after the Wright brothers actually built the first airplane. In 1914, Curtiss in the C-2 biplane literally created a wing leveler, which is basically a feedback control scheme to basically keep the wings level and reduce the load on the pilot. Because for those of you who fly, you quickly realize that trying to manually control an airplane through an entire mission can be quite an exhausting exercise. And people have been known to leave cockpits of bombers in World War II absolutely drenched with sweat. And so then in 1931, the Curtiss again, the Condor, the fully licensed autopilot to maintain attitude in the airplane. 34, we had the auto tune radio. So basically allowed you to switch from station to station without having to basically have somebody manually tuning the radio. And then in 1947, an auto trim, first fly-by-wire airplane in 1958, quite early. Flight director in 1955. Full first Cat-3 certified flight computer in 1972. And of course, the modern flight management system in the Boeing 767, 757, the first FADEC, which is the ultimate in terms of guaranteed safe autonomous systems. And then of course, the GPS Garmin receiver in 1994. So in a little bit over 100 years, we went from nothing to a whole lot in terms of automation. And that has enabled a reduction in the flight crew complement that's required. So very early on, you need to have 5 people in a cockpit. And so the cockpits then back in the Boeing 314 was quite an expansive affair. You had to have a radio operator, you had to have a navigator, you had to have a chart plotter, and then you had to have the pilots themselves. And so what happened was, first of all, you get the auto tune radio, which means that you didn't have to have somebody to literally sit there and sit and tune the radio. So you could reduce the flight complement from 5 to 4. And then in the 60s, you then made the argument because of the Lorentz system was commissioned and we got experience that we could reduce it to 3. And then we had all the systems in place back then for us to go to two-person cockpits. But this became a very political issue about whether we should have 3 or 2. And the one thing that had to change for that to happen was the fact that we had to figure out new ways for the pilots to interact. Because when you had 3 people, you had a nice system set up for parity testing. If the captain went bonkers, 2 people could override the captain. When you have 2 people, it becomes more of a teaming effort. And so there was a great deal of work done in new crew management and crew resource training to reduce the cockpit crew to 2 people. And then we all know now that we're having lots of discussions about single pilot crews versus no pilot crews, full autonomy. And the bottom line is that we're at the point where we have to be moving from just automation to really what I refer to as true autonomy. So what is autonomy? So most people consider a system to be autonomous if it can do all the tasks that you ask it to do without human interaction. So in many ways, the problems we've talked about before, and the problems we'll talk about for the remainder of today and tomorrow, we are asking the machine to execute a finite set of tasks using predetermined rules. So autopilots, cruise controls, parking, the DARPA Robotics Challenge, Lars system, there we all specified at relatively high level, but still low level, still low enough of a level, specific tasks, and then we actually ask the machine to follow those tasks. And this is, in my mind, predicated on a view that autonomy is based on action. It's basically being able to operate independently of humans. But if you look at the dictionary, which is always a good place to go, autonomy is really a quality of state of self-governance. And so I'm going to take that and talk a little bit about what does that really mean. Well, if you think about it, self-governance requires autonomous decision-making. And what it's more than just being able to operate autonomously from human intervention or interaction. It really means being able to make decisions in situations that you have not been exposed to before. And that for me is the great sort of challenge or holy grail for autonomy, which is how do we develop systems that can think for themselves, albeit within the context of some overarching goal or objective, and move away from just basically having rules that are prescribed by the designers of systems, and we certify will perform in a certain way, and then we get to the boundaries, we basically go put our hands up. So how do you tell what autonomous decision making is? And so I like 3 o'clock in the morning test. Anybody who's ever taken a class with me always know that I come up with one, which is somebody wakes you up at 3 o'clock in the morning. I'm being recorded, but they put something to your head and they basically tell you, all right, here's your system. It's in this internal state. Here is internal state matrices. Here's the external operating condition, and it asks you what the system will do. If you can answer that question, this is autonomous operation. If, however, you're not 100% sure because you don't know what experience that system has had since the last time you interacted with it, right? Then that's autonomous decision making, because you cannot predict what the system will do with 100% confidence. And so in a sense, what we have is that autonomy, which we often think about as being a one-dimensional thing, is really 2 dimensions in my mind. There's the decision and there's the action. And the decision can be made by either the human or the autonomous machine, and the action can be made, executed by either the human and machine. And so we have sort of 4 sort of canonical instances of what autonomy is. And the more you get, as you go from 1 to 4, you basically get increasing levels of autonomy. And so one example of instance 1 is the one here shown here, where somebody is manually flying a hang glider, where the human is clearly making all the decisions and the human is clearly executing all the actions. But then we have instance 2, where the decision is made by the human and you can execute, the machine executes it. And so this is a cockpit, and everybody would think that this is a very highly, automated or function, but it really is automated in the activity. But in the end, the pilot is specifying either a trajectory or actual next states, that target states that you want the airplane to do. And then the airplane is responding and executing because of what the pilot has specified. One thing that gets close, where we have the decision being basically made by automation. But then the human becomes an executor as TCAS or ACAS X or whatever version it is, where you have the machine there, but the human is making the actual execution. Now, I'm still trying to find a good canonical example. So this is one thing for folks in the audience. If you have one where it's in aviation, where the machine decides everything and the machine does everything, please let me know. But that's really, as I said, the Holy Grail. So with that said, I will end this section, which is what is autonomy, by saying the following. Full autonomy requires both autonomous decision-making and autonomous operation. And we need to expand our viewpoint a bit to really think more and more clearly about incorporating decision-making as part of how we classify and develop autonomous algorithms. And the one thing that over the past few years that struck me is that the organization, and I'll come back to this in the next section, it does a really good job of managing autonomy within the construct of overarching objectives, the military. And so one of the things I had when I was at UTC was that we went to one of these training programs at the West Point, and we learned a lot about commander's intent. And so my poor students have been suffering since I've been back in academia from this. But in the commander's intent is you define and describe what a successful mission is. You don't tell your reportee how to do the mission. You tell them what you need done, when you need it, and what the measure of success is. And you leave the decision about how to do it to the reportee. And my premise is, and my thinking is, and I don't have anything to report right now, but we're doing work on this, is a way for us to enable autonomous decision making, which is taking the prescription and the description of the task that of the job that needs to be accomplished, as opposed to the tasks that need to be done, and using that as the basis for specifying and setting requirements for autonomous systems. So I remember earlier, Claire, you were talking about in the second talk about that. I think that this is the way we need to be thinking when it comes to moving forward in autonomy. So now that I have hopefully convinced you that we need to expand our definition of autonomy a bit, I wanted to go on to talk about some of the policy implications of this. So one of the things that we looked at in about 2014, a few years ago, was I was co-chair of the committee, National Academies Committee, who came up with the sort of agenda for autonomy research in civil aviation. And what you see here are sort of three categories of barriers. Technology barriers, and I'm sure everybody here is quite familiar with those, communication and data acquisition, cybersecurity, cyber-physical security, diversity of aircraft, managing all the different types of aircraft, human-machine integration, et cetera, and V&V, of course. But there's also these regulatory and certification barriers. So how do you give access for unmanned vehicles, the certification process itself, which is more than just V&V, how do you define equivalent levels of safety for autonomous system? And last but not least, in the regulatory and certification area, trust. How do you engender trust in non-deterministic adaptive systems? And that is the launching point for my discussion here in this section about policy, which is certification is really, really hard and difficult because the real world is stochastic and it is not scalable for us to define every possible input-output condition to prove the behavior. And so we cannot guarantee that we'll always make the optimal decision or even a safe decision by doing this enumerative type scheme. So the question then becomes, are there instructive human certification examples? Because humans are inherently autonomous decision makers, yet we certify them all the time, right? In fact, we certify our own kids. So, you know, this is my notional chart for the level of trust in terms of how much you allow your kids to operate autonomously as a function of your trust in their judgment, right? I'm still trying to adapt this curve. I have two 13-year-olds, they're behind me and in the picture behind me. And I'm still trying to figure out where they are on this curve. But this is the notional one. Maybe in a few years, I'll be able to answer and fully flesh out my own experience with this. But the truth is, you never quite trust. I don't think my parents trusted me 100% when I left the house. And so there's always a trust deficit. But the fact is, you need to develop an understanding of how people think and how they make decisions. And I think back to all the qualifying exams I'm given. We're not really testing how well people remember stuff. We're really testing how they think about and their logical structure. And that is also true in the military, which is the fact that nobody trusts a private to do anything much except point a gun in the right direction and shoot. I mean, it's in wartime. I trust them for a few other things. But you get promoted in the military not only because, and not primarily because you're good at doing specific activity, you get promoted because you have demonstrated good judgment. And so somebody who is very good at understanding the battle situation or just the life situation and makes what in other people's judgments are good calls might end up becoming a sergeant, right? Which is the backbone of the military anywhere in the world. But somebody who is really able to take abstract goals and convert those goals into specific sets of goals and decompose that high level goal into goals for people within their chain of command would end up, the people who are best able to do that end up, especially in the officer corps, as generals, because that is really the task of a general, knowing what the objective is and decomposing those objectives into sub-objectives, which then the people under his or her command can then execute, and tying all those in to meet the overall goal is really the challenge. And so that really is how the military thinks about certification, is again, measuring how people think. In aviation, back to the main thread, we certify pilots every day. And we give them licenses based on a check ride, based on an evaluation. And we evaluated them for continued employment and promotion in simulators. I will tell you that I have never met anyone who's been through every possible scenario that they could go through in a cockpit in any airline that I've worked with. But we certify them because of what we think is their judgment in a representative set of scenarios. So Michael Bragg, who used to be the dean in Washington, told me this one day. We were in a meeting and he said, when I was 16 and I was taking my check ride, we're rolling down the runway and the inspector opened the door when we were about 40 knots. This was like an Cessna 152. And he asked, so what do you think he was testing? Well, he was testing your ability and to basically assess the situation, understand whether or not there was some issue that would be there and whether or not they should abort the takeoff or not, right? And so in the end, autonomous agents need clear, measurable objectives. We talked about that. But they must also have the following. And these are the things that they need to be able to take those objectives and develop them into meaningful plans or actions. Know themselves and their environment. So able to estimate their own system states and the states of their operating environment to high confidence. Notice I use the word confidence because it's not something that's going to be 100%. They must be able to take actions that will result in an outcome that's better than doing nothing. It's I call it the Hippocratic Oath approach, which is to do no harm. And you can see Asimov is running wild through these three things. And then, of course, protect itself. Take only actions that would keep their capabilities above a certain level. So in the end, when you're thinking about what autonomous systems need to do and what policies you need to develop, we need to think about what level of capability in each of these areas is required. In a sense, we need to figure out how we can measure the ability of a machine to make a decision given clear goals and objectives, and how good they are at estimating internal and external state variables. And it doesn't have to be 100%, but if it's 80%, that's a machine that I can trust better than something that doesn't know how to its own states at 20% to 80% of the time. It doesn't know its own states. So if it knows it 80% of the time, it's better than somebody who doesn't know it 80% of the time. And the same is true about defining your action sets and protecting for protecting yourself and doing no harm to others. So again, how would you do this? Well, I do stochastic programming. So one would expect that I would think that we developed some Monte Carlo simulations, and we've been doing some work on this to figure out the percentage of time that the system is correct, right? And the fact that the percentage of the time that it actually fully defines the state of actions that would keep it safe and do no harm. And then what you can do is then do sampling-based stochastic programming to determine the set of actions, the best set of actions over the short-term time frame that would keep the system safe and do no harm. So one question that leads to, for those on the call, what should the machine do when there is no feasible solution? I'll be honest with you, that's not a question that I have an answer to. And I think that's an ethical question that, again, we need some work to do. But I'll tell you what we do in aviation with humans. In aviation, we are required to abort a mission if we have determined that we're about to lose our last fallback option. So a principle that you see from a policy perspective, and this is something I think we need to be discussing more broadly within the context of autonomy, is how do we preserve options, and what policies and what kind of designs do we put in place to basically determine what your backup options are and make sure you always know that you have at least one backup option left. And after that, we need to figure a way to do what the pilot does, which is evaluate and determine what the appropriate response should be if you have no options left. And that way, I mean, no safe options left, the ones that do no harm and keep you safe. And so that's going to be an ethical thing. I mean, right now we basically leave it to the pilots, but we do need to have policies around how we train and evaluate these autonomous agents, which will be machines in the systems we're talking about. The last bit I wanted to talk about was system safety. And since Lars was coming before me, I decided to do a problem, which was a landing problem, but I'll do it for airplane instead, because I don't do rockets. So landing and approach and landing in aviation is a very challenging operation. Not quite as challenging as landing a rocket on its tail, I will admit that, but it's still challenging because there actually is, to this day, significant risk of missing the runway due to pilot error, system error, or rapidly changing winds. And the way we deal with that is that we require ground or satellite-based guidance systems to complement the onboard systems. And we also require obstacle clearance zones. We basically make space. And together, these other systems, not on the aircraft, and the real estate we tease out or block out for the vehicles, together give us the ability for the pilots to determine before they commit to a landing whether they can reach the runway safely and whether the runway will be clear so that if they get there and they have to avoid an obstacle, they can either brake in time or do a takeoff from just after touching down. So an execution maneuver, right? And so how does this happen? Well, we have the most common landing system is the instrument landing system. And I won't go into the details of this, but the bottom line is these are basically beacons that give you a path. The glide slope gives you a path about nominally 3 degrees down to the runway. And you have a localizer antenna, which you probably have seen at airports, but I bet not many people realize what they were. These basically give you the guidance for the track of the center line of the runway. And then you have a couple of beacons which give you some signals to tell you how far you are from the runway. And together, these subsystems allow you to guide you down to the runway. The other thing that we have is that we have these obstacle clearance zones, which basically specify, and you can see them here, that nothing should extend above the top of this surface, that looking like a tray here, a depressed tray. And that allows you to deal with all the uncertainties in the aircraft trajectories, and so that you don't run into buildings or trees, etc. So again, together, they give you a zone where you can deal with the uncertainties. So all this together, when we operate, we have what we call missed approach criteria and the procedure. And they have 3 different levels: Cat 1, Category 2, and Category 3. And Category 3 has 3 different capabilities. I won't go into the details for the interest of time, but I will say the following. Each of the categories come with a separate ceiling and visibility requirement. And the interesting thing about these categories is that the visibility and the ceiling requirements are dependent on the precision of the ILS system at each airport and the training of the crew. So what does that mean? If you don't calibrate your system every week or twice a week as you're required for Category 3, you will have to operate a Category 2 or a Category 1 system, which means that over the time, the uncertainty in your system, well, it will drift and become higher. And so that what that means is that your uncertainty about where you are based on the instruments inside the cockpit would actually be higher in a Category 1 system than in a Category 2 system, and even higher in a Category 3. What does that mean? That means that you set your decision height to the point where your endogenous uncertainty is so large that the landing can no longer be guaranteed. So the reason why we have a decision height is that we're literally waiting for a visual cue, i.e. to be able to see the runway or the landing lights, to confirm that our uncertainty is small enough and we are able, based on where our position is, to make it to the runway. So it's a trade-off, right? You have an uncertainty. The closer you get to the runway, if your uncertainty is really big, you could be off to the left or the right of the runway, or well short of the runway. So given that and the response that you have, you need to make that decision to commit to the landing earlier, and you also need to have the visual cues to confirm your endogenous states earlier. And so we can think about this as a reachability problem. And I won't go into that details. I won't go into that now, but this is an idea that I think we need to be exploring as well. So how do you tell if you're uncertain to do great? Well, basically, you just basically look and say, based on where I am relative to the nominal path, either to the left or the right, above or below, if I am in the worst case uncertainty, can I make it to the runway? Or more importantly, and a lower bound, because I have my obstacle clearance zone, can I make it to a point where if I do touch the ground, there's nothing to me. So the part of the thing about having the obstacle clearance zone on each side and the clearway on either side of the runway, or the runway zone leading in, is that you could execute a missed approach. You may just touch the ground, but because of the obstacle clearance zone, you're guaranteed not to basically run into an obstacle. And so again, you can see how those 3 things together, your onboard systems, your ground systems, and your clearance zone work together to provide a certain level of system safety. Which brings me to a question which I've been pondering for a while, which is, there are a lot of work being done in aviation to have different type of sensors to replicate what the pilot is doing. Do we really need to do that? Would it be better and more cost effective, and from a system perspective, better, more appropriate to put in cheap terrestrial systems to check the position, to offer an independent check of position to confirm that my onboard sensors are correct, and also to check to see if the runway is clear. So what I was saying here is that in aviation, you can see from this example, in part, we certify machines and people based on their ability to determine when they're about to lose their last option. And that's true for the landing problem I just described. It's true for flight dispatch problems. It's true for takeoff balance field length calculations. It's true for trajectory planning in flight. All of these, we always rate people first, and we rate our systems, including machines, based on their ability to determine when they're going to lose their last option, and we build them such that case. So in summary, because I wanted to make sure I stick with half an hour, to my mind, full autonomy requires both autonomous decision-making and autonomous operation. And I think we need to structure our thinking in that way. To make autonomous decision-making work, we need clear commanders' intent. And these, they could be, you can think about formal specification languages for commanders' intent with respect to autonomy, but that's an area I think we need to, as a community, be working on. We need to think about policies where we have clear objectives and constraints, and that systems must always make sure that they have a fallback option. We need an ethical framework for training and evaluating autonomous agents. We have one for pilots, but we need to figure out a parallel one for machines. And we ultimately need to measure the ability of people and machines to determine when they're about to lose their last options, because that's something that if we're going to truly have fully autonomous systems that are going to be making decisions based on their experiences without human intervention, then we have to make sure that they understand, like pilots do, that they must have a last option available. Pilots, one last thing, pilots do that because they want to stay alive. I guess we should try to figure out how to inculcate machines need to stay alive and figure out that they always must have a last option. So with that, I will stop.